Hello, we have another piece of precision vintage gear for repair. This is a 7.5-digit multimeter by Datron. The model is 1071 and I think it was made in mid-80s. This unit is in a fine shape considering the age, and it has nearly all the options installed. It must have cost a fortune back in the day. I got it from eBay for slightly more than $200 delivered, and because it's not working properly, and I believe it must be an interesting project. So let's try powering it up. And there you go. I have never seen this state. I already played with it before, and it powered up with various error messages, and the controls were not quite responsive sometimes. Sometimes it looked like the unit just locks up and does not respond to any controls. So this time it did not even initialize for some reason. But at least now we can clearly see that the display is bad. These displays tend to degrade over time, so that these segments are not fully visible. And when I bought the unit, I assumed that the display is completely dead. And now I'm glad that it turned out that it is usable, at least for now, for testing, so I don't have to start working on it right away. I have some ideas how to replace the display, but I can get back to this if we manage to repair the rest of the unit. Here is the back of the unit. Look at this. Datron Electronics Limited, Norwich, England. And here we have the list of options. Let's see. Option 10 is true RMS AC converter. Option 20 is 4-wire resistance measurement. Option 30 is current measurement, both DC and true RMS AC. Option 40 is rear input and ratio input, these two connectors. Option 50 is GPIB interface, this thing. Option 70 is analog output, this connector. Option 80 is 115 volt 60 Hz line operation for American market, I suppose. And option 90 is rack mounting kit. I'm not sure I have it now, but who cares. And this external trigger is option 52, but it's not listed here for some reason. Perhaps it is standard for this model. And here we read renew battery May 87. So the unit must be older than this. This is how it usually powered up, with fail message and hold enabled. And I sometimes could disable the hold with the first press, sometimes could not do it at all. Oh, now I did it in a few tries, so we can switch ranges, but it switched to AC for some reason, so something weird is going on. So this problem with unresponsive controls must be addressed first. Here it is with top cover off. So here we have power supply on the back, digital board here, analog board here, some option modules on the back, and look at this chip. Seems like a 28-pin chip with a heat sink on it. Here is a better view of the options on the back. And I know what you are thinking. Where is the voltage reference? And I think here it is. This pair of Zener diodes. Let's have a closer look. Here they are, with some tags on them. I think I can see some writing on this side. I can barely see something like 272, perhaps. Not sure what it means. And I don't see anything on the second tag. I removed the front panel. And this switch seems to be faulty. All other switches click, and this one does not. This is the bottom of the unit. There are 5 boards here. This one is GPIB. This one is display driver. And this one is resistance measurement module. This one is AC measurement, the true RMS converter. This one is current measurement module. So all these are options. Look at these tantalum caps. These are two identical 10 microfarad 25 volt capacitors, and one of them is clearly cooked. So let's put in a couple of new ones. Alright, a couple of new capacitors are installed. And by the way, so many plastic clips like this are falling apart, so that some boards are even held by plastic zip ties instead. For example, the GPIB board is held by this zip tie using this test point. Here is a good looking capacitor, about 0.5 ohms ESR at 1 kHz. And here is the one which looks burnt, about 3 ohms ESR. And here is a new one for comparison, also about 0.5 ohms ESR. This capacitor in the power supply has high ESR of about 5 ohms at 1 kHz. And this is a high voltage supply for the display. The capacitor is 10 microfarad, 450 volts, 85 degrees C, and it was replaced already at some point. Look at that soldering job there. So I found a replacement by Nichicon, same parameters, and it is quite a bit smaller. This guy has ESR of about 1.5 ohms at 1 kHz. And I also found this larger one, 68 microfarad by Rubicon. And this one is rated at 105 degrees C, which is better. And high capacitance should work just fine here, so I'm thinking about putting this one in. And this guy has even a lower ESR of about 0.7 ohms. 5 ohms was in circuit. Out of circuit it is even worse, about 7 ohms. That's pretty bad. I removed the calibration lock, and I was going to visit a locksmith just to see how expensive it would be to make a key for it. But then I managed to pick up a new lock in a local electronics store for just $4.50. Wonderful. I made this a special washer to keep the lock in place, that is, to keep it from rotating even if the nut gets a little loose. The old lock relied on this groove in it, and it worked like so. But the new lock has these flat surfaces instead, and there is this clip which goes with the lock as a part of the kit, but it won't work in this situation. And this little pin is supposed to go into that notch on the bottom of the hole. Let me put white paper behind so you can see that little notch. And here is the result. There is one more mechanical problem here. This is the bottom of the unit, and it has two shields. They are not connected to each other. This shield is for the analog section, and this is the overall shield of the unit. Here is the spring contact, and the similar contact here on this shield is broken off. And this is the only connection to this part of the chassis. This contact is supposed to touch this part. So I found this clip which should work perfectly, but I need to arrange a couple of notches here in the right places for these two little hooks. You see, little hooks on each side of the clip to prevent it from sliding off and falling into the unit. There you go, this should work perfectly. I have made a lot of progress here. First of all, I checked all the power rails and they seem to be fine. Then I decided to reseat all the socketed chips here on the digital board, except these two memory chips, because they are powered from this battery. When the meter is turned off, they retain calibration parameters and such. And by the way, the battery is doing great, 3.6 volts on it. So after reseating the socketed chips, that problem with unresponsive controls and locking up went away, and I have never seen it again. Then I started desoldering this faulty switch, and in the process the switch started working. So now it is clicking and working just fine, no problem anymore. Then I started studying the service manual, which is very good, with full schematics, description of operation, adjustment procedures and such. So I found that the fail message was about the corrupt calibration parameters. So I didn't really need to worry about these memory chips, because calibration parameters are lost anyway. So I found a procedure how to clear the calibration parameters. There are two pins here next to the processor. They need to be shorted when the meter is powered up, and that clears the calibration parameters. After doing that, the meter powers up with no error messages and seems to work just fine. So I started going through the post-repair adjustment procedure, And my first idea was to use this fluke calibrator, even if it's not really sufficient for the job, because it is just 6-digit and, simply speaking, 50 ppm unit. But this is the best reference I have at the moment, so I started adjusting the meter according to this calibrator anyway, thinking that later on perhaps I will find a better reference and recalibrate. But I could not even finish the post-repair adjustment procedure. The last step there is to set 10 volts on the calibrator, and then press this gain button in the calibration mode so that the meter is set to 10 volts. And then we are supposed to set 19 volts, and this will take a while to settle because of this filter, which is some sort of rolling average, but it has to be enabled to have the 7th digit. So we are supposed to make sure that this 6th digit is within 5 counts, and the 7th digit does not show up in the calibration mode. And as you can see, we are way more than 5 counts out right now. So this reading needs to be subtracted from 19 and the resulting error divided by 2, and then we need to set 10 volts again and adjust this trim pot here by that amount. And I tried doing that, but hit the limit of the trim pot. And there is a factory selected resistor on special standoffs close to that trim pot. It can be adjusted to shift the range of the trim pot if necessary, but I don't think it is a good idea. If you have seen my repair video of this fluke calibrator, you probably remember that I found the calibrator to be in spec with no adjustments at all, just after replacing a few failed capacitors. And I checked it using my Hewlett-Packard 34401A 6.5-digit multimeter, and I also compared that with a newer model, which is Agilent 34461A, and that one was in calibration by Keysight, and the meters agreed very closely within a few ppm. So the fluke was in spec, but that really means within, let's say, 50 ppm or so, which is not really enough right now for calibrating this meter. So I think to proceed with calibration I need to trust my Hewlett-Packard meter instead of this fluke calibrator. The Hewlett-Packard meter is also more accurate according to specs than the fluke calibrator. Simply speaking, it is a 35 ppm unit. This is called basic DC accuracy in the manual. Here it is, my trusty Hewlett-Packard 34401A meter, and as you can see, according to this meter, the 10 volt setting on fluke is about 4 to 5 ppm out. So let's set a 10 volt range on Datron according to this meter. First let's do the 0, which is done by applying a short piece of copper across input terminals. And let me turn that key on the back. to calibration. As you can see, the 7th digit disappeared. So now we are in the calibration mode, and we are supposed to see cal indicator here, but this segment is not doing very well on the display. So we don't even see that cal. Anyway, it is very close to 0, so nothing to do here, but if we needed to set 0, this button should be used. There are red labels here which apply in calibration mode. So now let's remove the shorting link and connect the calibrator again. And now there are two ways. One is to adjust fluke until we read exactly 10 here and then press gain. Or there is another way. If the reference is not exact, we can just enter manually, like so. 10 0 0 0 0 5 and then press gain. So when this light disappears, we should be done. That's it. Full scale is set. So now let's check the 19 volts. And I already adjusted that trim pot inside so that this matches Hewlett-Packard meter very closely, as you can see, 99899 or something. And because this display is bad, it's sometimes hard to tell 8 from 9. I don't want to bore you with details. I went through all the ranges and all the modes and set Datron according to my Hewlett-Packard meter. I could not calibrate a few things, let's say high voltage AC, 100 volts and 1000 volt ranges. I could not find appropriate reference. Lower AC ranges I calibrated using my Hewlett-Packard function generator. I measured the output with the Hewlett-Packard meter and then transferred that reading into Datron. So now Datron pretty much should be as good as my Hewlett-Packard meter. I finally got myself a GPIB to USB adapter. This is one of those believed to be fake Agilent adapters sold from China all over eBay. And prices went down recently. They used to be more than $100. I got this one for about $70 or maybe $75, I forgot. So I want to run an experiment. I also have this GPIB cable, so I can connect both meters to my computer, collect data and see how the meters drift and how fluke drifts with temperature and with time. Unfortunately, I don't have any source of temperature readings at the moment, so I'll connect all this and run the experiment, and we will see what happens. So here I set up Linux GPIB package to support the adapter, and I wrote some code in Octave, which is free equivalent of MATLAB, and I'm using instrument control package in it to communicate with the instruments over GPIB. And here is my data collection and graphing going on, and I also saved the readings to a file. And this was going on for more than half an hour, 0.6 hours so far. The blue line is Datron and the green one is Hewlett-Packard meter. And currently each division, vertical division, is half a ppm. And as you can see, Hewlett-Packard stayed within ppm and a half or so. And Datron stayed for the most part within this ppm, well, slightly. Let's call it ppm and a half as well, except this initial jump. For some reason it always does this. Starts a bit lower and then in a few readings stabilizes higher. So I will run this for a while, let's say overnight, and we will see what happens. Here we are in about 17 hours. As you can see, there is some drift, and most of that must be the temperature drift, of course. The temperature here in the lab changed in the range from about 16 degrees to 30 degrees C, or in Fahrenheit from 61 to 86 degrees. And now the vertical scale is 1 ppm per division, and the meters are running about 2 ppm from each other. They started about 1.5 ppm apart, and I believe this is not bad at all. I'm quite pleased with the result. I let this run a little longer, so now we have about 28 hours of data, and the meters seem to have drifted apart a little bit more. Now they are running about 2.5 ppm apart, which I believe still looks quite good. Even if we assume that the Hewlett-Packard meter is perfect, this means that Datron meter drifted up about 1 ppm in 28 hours, which is well within specs. Here are the specs for Datron 1071: DC voltage, accuracy 24 hours at 23 degrees C plus minus 1 degree, 10 volt range, 3 ppm of reading plus 2 digits, 90 days 15 ppm, and 1 year 20 ppm. So in this case we did not hold the temperature constant, so it was not really a properly controlled test, but given the equipment I have and the environment I have, the results I think looked quite good. I know I am assuming a little bit too much here. There is a small chance that all 3 units drifted a lot, it just happens to be the same direction. But I think we will have to take some chances, otherwise we will never get anywhere. So, what's next? I have a couple of projects in mind. One would be to replace the display somehow. For example, hook up a microcontroller, either instead of the whole display board, or maybe right at the output from the display board, capture the data, decode, and send to some other display, which should be fitted in place of the existing one. This might be a challenge, but I have some ideas about that. Another project would be to arrange an accurate temperature sensor connected to the computer, so I could graph the temperature together with the voltages. I think it might be interesting to see the correlation. So, if you are interested in watching this sort of stuff, leave comments, subscribe to the channel, and give this video a thumbs up. Thank you very much for watching, and I hope you will watch the next one. Goodbye.